All right. How's everybody doing today?
Good.
Hanging in there? Okay, good. All right, cool. So I wanted to start today with, well, we're going to be covering a few things. I wanted to start with an announcement about the next couple of classes, and then I'm going to go over just a brief reflection on the midterm. I'm not going to cover in depth, how to answer, how to figure out the circuit, but I just wanted to talk a little bit about kind of what the midterm means in terms of your grade and things like that. Then I want to go on to our main topic for today, which is our lecture. So we're going to talk about the oscilloscope and function generator today. This is super cool. These are some of the types of instruments that you will be using out in industry. So these are great for test and measurement of circuits. So we'll talk a little bit about how they work and what they can do for you. So we'll start with the function generator. We'll talk about what it is, why it's important, and how we use it. And then the same thing for the oscilloscope. And then we'll do a preview of today's lab. And for homework, I'd like you to work on the oscilloscope crossword, which is on page 127 in your lab book. So any questions before we get started? All right. So then let's start with some announcements here. So starting next Tuesday, we're going to split the class apart for about 5 sessions worth, 5 days. And the reason for this is because we're going to start learning about soldering, and we have a soldering lab over there, but it only has room for about 24 people. So we can't fit the entire class in the soldering lab all at the same time. So what we're going to do instead is that starting next Tuesday, we're going to split the class apart, and half of you will spend the next 5 lessons learning about soldering. The other half will spend the next 5 lessons learning other labs that we would be doing in this semester. And then after that, you'll switch over. So the people who are soldering will start learning about the other labs. The people who are doing the labs will go and switch back and do the soldering. That way everybody gets to do everything, and we have enough room for everybody in the soldering lab. Does that part make sense? Cool. So on Tuesday, if you normally sit in Fred's section in the lab, you'll just go over there at 9 o'clock, and Fred is going to do the lecture for you. I think we're going to start with advanced digital multimeters. So he's going to talk about that starting on Tuesday. So if you're normally sitting in his section, you'll just go over there and do that on Tuesday. If you're normally sitting in room 409 with me during the lab, on Tuesday you're going to go over into room 411, I believe, over across the way. Or actually, no, I'm sorry. You'll just come here. We'll do the lecture in here because that space is terrible for lecturing. So we'll do the lecture in here about soldering, and then we'll move over there and actually do the soldering itself. Okay? So again, starting on Tuesday, if you're normally in Fred's section, you'll just meet over there in his room at 9 o'clock. If you're normally sitting with me, you'll meet here at 9 o'clock as we normally do, and then we'll do the lecture, and then my class will go over and do the soldering. And then, like I said, after about 5 classes, we'll switch around, and you'll get to do the other thing. So any questions about that? All right, and I'll try and send out a reminder to make sure everybody's on the same page. So if you're sitting in my section and you're going to be doing soldering on Tuesday, then please bring some safety glasses if you have them. So the safety glasses look like this. You can get any kind of safety glasses are fine. You can get them at the bookstore. You can get them at a hardware store. Anything is fine. The only thing is that just plain reading glasses or eyeglasses don't work because they don't have side shields. Yeah?
For what it's worth, if you're like me, you need glasses to see up close. And
Yeah.
at Walmart, they sell them pretty cheap, but they also have some safety glasses that have some magnification built in, which are really nice.
Oh, there you go.
If you need it.
Yeah, good tip.
So
Yeah.
that's what I have. And you get them there, they come with a nice case. I think they're $5 or something like that.
Nice. Okay. Well, yeah. So perfect. So if you have some safety glasses or you want to get some with magnification, sounds great. You can bring those. If you don't have any and you don't want to get them, I believe that we have some that we can give you. So I'm pretty sure that Stan
I
had
don't
some.
know. The
Yeah.
ones that you get will probably look like they've been cleaned with sandpaper.
Well, yeah.
Yeah.
I think we had some to give out. Like,
Maybe they do now.
yeah. So, so that was that. So, any questions about any of that? Okay. So then, so I just wanted to talk briefly about the midterm. So the first thing that I wanted to say about it is that it's not a huge number of points. It's 20 points, which is the same as 2 labs. So it's not going to make or break your grade in the class, and it's not designed to. It's not supposed to do that. So the thing that I think the midterm is good for is just kind of a check-in. Check in to see how you're doing in the class and how these ideas are sitting with you. So, so when you think about the midterm, what I would say is think about how you did. So if you got a score that you're happy with, then that's great. You know, keep up the good work. You're doing great. But don't forget this material because we are going to do something very similar to this on the final. Okay? So if you have a score that you're happy with, that's awesome. Keep up the good work. If you took the midterm and the score wasn't quite what you were hoping for, I would say this is a good time to kind of check in and think about what happened. So there's a couple of ways I think that people can get scores that they weren't looking for. So the first thing is kind of a technical problem. So maybe you were taking your test and you meant to type in a decimal point, but you hit a comma instead. You know, it's an easy mistake. You knew the answer, you knew what it was supposed to be, but you just pushed the wrong button. No problem. If that happened to you, let me know. I would like to try and fix that, okay? So if it's just a technical issue, that happens all the time. Don't worry about it. Let me know. Another situation might be that you went into the midterm and you got an answer that was wrong, but you looked at it afterwards and you went, of course, I know what happened there, you know. And so you figured out what went wrong and you know how to fix it. Well, if that happened to you, congratulations, that's learning, okay? that's what we're here for. Like I said, that, you know, if you lost a point or two on the midterm, but you figured out, you know, what's going on, no problem, that's fine. Another thing that can happen is you went in and you felt like you were feeling pretty confident, and then you took the test and you realized that you didn't know how to get some of the answers, and you came out and you still weren't quite sure how to figure out some of those answers. And that happens too. And that's fine. That's one of the reasons that we take this midterm, is to really kind of check our own knowledge and see how we're doing. And if that happened, if you're still not quite sure how to get some of these answers, this is a great time to come and talk to me. In fact, after class today, I'm going to do a review for the midterm. So if you did the midterm and you weren't able to figure out some of the answers and you want to have a little bit more information about that, I would say try and stick around after class today. I'll be in the lab room over there, and I'll go through and do a bit of a review of that starting at noon. Okay, so if you're interested in that, please stick around. I'd be happy to talk to you. If that time doesn't work for you, let me know, and we can find a time that does, because this is important stuff. Like I said, we're going to be covering a very similar problem on the final, and so it's important to understand how this works. And really, this is the fundamental knowledge that we're trying to teach in this class. You know, how to look at a circuit, how to build the circuit, how to measure these voltages and currents, and how to figure these things out with formulas as well. So this is really important stuff. So please make sure that you understand this. And like I said, it's going to be on the final as well. And I've had many cases in the past where people do well on the midterm, and then we start talking about other things in the class, and we get to the final, and the person who got 100% on the midterm, you know, gets maybe 75% on that question on the final because they, you know, they weren't thinking about it or they weren't practicing it as well. So please make sure that this kind of stuff is really, really clear in your minds, okay? Because this is important. So, so again, the midterm's not going to make or break your grade, but it's important that you really understand it. So please see me if anything is not clear there. Okay. So any questions about that?
I just wanted to say, Jordan, that during Open Lab too, anybody can come in and I can help, you know, with the circuits and doing the math on that as well.
Absolutely, yeah. Steven's a great resource, and he does have the open lab times on Tuesdays and Wednesdays from 12:30 to 2:30, and I'm sure he'd be happy to spend as much time as you need to go through all of the circuits and make sure that everything is, you know, you get as much practice as you need and everything is super clear, right? So yeah, great resource. So, all right. So that's what I wanted to say about the midterm. So let's go on to our main topic for today, which is our lecture about the oscilloscope and function generator. So we're going to start, so these are two pieces of test and measurement equipment that are used all the time in the real world. And we're going to start with the function generator. We're going to talk about what it is, why it's important, and how we use it. So what is it? So a function generator is a little piece of equipment, looks like this. They often sit on a bench top like this. So a function generator creates electrical signals. That's its fundamental purpose, to create electrical signals. So it can create all different kinds of signals. They might look like this, or like this. They might be different sizes, so that some of them might be, you know, really small, and others might be super large. But it creates these electrical signals. Okay? So that's what it is. So why is it important? Well, they're used for testing circuits. So let me give you an example. So say that you are building some pedals for an electric guitar, an effect pedal, okay? So say you're working at a company, it's building these effect pedals. So you put the circuit board together for a particular effect pedal, but then you want to actually test that pedal and make sure that it's working correctly. Well, what do? So, I mean, sort of the first thing you might think is that it's an effect pedal for a guitar. Maybe you'll just plug in a guitar and strum a note, and then look at the signal that comes out. Well, that would be one idea, but there's a couple of problems with that. First of all, when you strum that note, well, basically, when you're looking at the output, you want to see a couple things. You want to know maybe how much amplification that pedal created, and any other sort of effects that pedal might have added into your signal. Well, when you strum your guitar, every time you strum it, it's going to be a little bit different. Sometimes you're going to strum it a little harder. Sometimes you're going to strum it a little bit softer. Sometimes you might strum it in a different place. So every time you do that, the incoming signal from your guitar that goes into that pedal is going to be a little bit different. That means that it's going to make the output signal a little bit different also. And if you're just looking at the output, you'll have no way of telling whether those differences are coming from the way that you strummed your guitar or from, a problem or a difference in the actual board of your pedal. So what you want when you're testing this pedal is you want the input to be super consistent, exactly the same every time. That way, when you look at the output, if you see any differences in the output, you know that they're coming from the circuit board itself. So when you're testing this guitar pedal, you need the input to be super consistent. So that's what a function generator is good for. The signal that comes out of an electric guitar when you strum it is essentially a sine wave. It's a wave that looks kind of like this. Well, your function generator can create exactly that type of wave. It can create a sine wave, and what's more, it can make exactly the same type of sine wave, and it can make that sine wave last as long as you want. When you strum a guitar, it lasts for a couple seconds and then it dies out. This sine wave can last as long as you want, minutes, hours, days, as long as you need in order to perform the tests that you want on that pedal. And this is true for many other types of circuits as well. If you are testing a radio receiver, you might be hoping to pick up radio sound, signals that are coming out of the air, but those signals might not be consistent. So instead of using an antenna to try and pick up whatever signals are around you, you can use a function generator and attach that to the antenna port, and then get a known fixed signal coming into your radio receiver circuit and use that to test your radio receiver. So these function generators are great for creating these consistent signals that can be used to test out various types of circuits. Okay? So that's why we use function generators. Any questions about that? Okay, so then how do they actually work? Well, the generator has it has three main controls on it. So you can adjust three things. So the controls, number one is the shape of the signal. So when I say shape, I mean one of these shapes. So you can choose this top shape, that's called a square wave. This middle shape is a sine wave. And the bottom shape is a triangle wave. So that's the first thing that you can control with the function generator. You can choose what type of wave you want to make. The second thing you control is the amplitude. The The amplitude is how big the wave is. So it could be a small amplitude like this, or it could be a large amplitude like this. And then the third thing that you control is frequency. Frequency is how often that wave repeats. So you could have a fast frequency like this, or you could have a slow frequency. It looks more like this. So you can see I tried to make the amplitudes of these waves about the same, but the frequency is very different. So this first one happens very quickly, very often, high frequency. And the second wave takes a long time to repeat, so that's a low frequency. And I will show you where these actual control buttons and knobs are when we do the lab preview. Yeah?
You said how often, frequency, how often, what? I couldn't hear that part.
Oh, it's how often the wave repeats. So what this, yeah. Okay, so what the frequency refers to, if you could look at this wave and kind of see that there's one shape that happens over and over again. So you could say that, you know, from the top point to the next top point, that would be one wave. So the frequency is how many of those waves you get per second. So one wave is referred to one cycle. So frequency is given in cycles per second. So I should label my axes here. When I'm drawing these on the board, the vertical axis here is voltage, and the horizontal axis is time. So let's say that you have a wave here, and maybe it's a triangle wave. And let's say that this is 1 second right there, and then right here is 2 seconds. So let's try and figure out the frequency of this wave. Well, we can see that it starts right here where the wave is kind of angling up from the middle line. So we have to find the next time that happens, and that will be one complete cycle. So I look around here, we get to the line here, but now our signal is angling down, so we're not quite back to the start. So here, that is when we get to the point where the line is angling back up just like we started out. So from there to there, that is one cycle. Okay? So that's one cycle. And then we're here, and then that is right there, that's another cycle. So how many cycles are there in 1 second here? 2. So this wave has a frequency of 2 cycles per second. And cycles per second is also called hertz, which is abbreviated Hz. So that's how we get cycles per second. Yeah.
I don't know if I'm wrong, but why do a lot of people that I know interpret like higher frequencies as like a higher pitch or something like that?
Yeah, so it is. So sound waves are, so sound is really just pressure. It's air pressure. And sound waves are variations in air pressure. And a pure tone in a sound wave is a pure sine wave. And the higher the frequency of that sine wave, the higher the pitch that we hear.
Okay.
Yeah. So yeah, people will often refer to sound as high pitch or high frequency, or low pitch or low frequency. It's really talking about the frequency of the pressure wave that's hitting our ears.
Do you know what frequency the average person can hear?
Yeah, so the frequency range of hearing is typically, for very good hearing, it's about 20 hertz to about 20 kilohertz.
Huh.
Yeah, that's excellent hearing. As people grow older, their higher frequency hearing typically diminishes. So, but that's about the normal range for human hearing.
That's from damage, right?
Yeah, from exposure and just life, I think. Yeah. So if there are pressure waves in this frequency range, then people can typically hear them. Outside of that range, we can't. And maybe sometime I'll bring in a speaker and we can actually hook it up and hear it. Yeah.
In the context of power, the amount of cycles, does that relate to current at all?
The amplitude relates to the volume of the sound, and also it's the voltage which regulates the current in the speaker. Yeah, so the higher the amplitude, the higher the voltage, and the higher the current. Okay, so let me just get back to frequency for a minute here. So we said that the number of cycles that you have in every second gives you the frequency. You can also tell that there's sort of a relationship between the the length of the cycle and the frequency. So the shorter the cycle is, the more of them you'll get in a second, and so therefore the greater the frequency will be. So there's a formula that you can use. So if you know the period, we can say that the frequency is 1 divided by the period. And also, we can say that the period is 1 divided by the frequency. So let's see how that works here. We said that the frequency here is 2 cycles per second, or 2 hertz, so we could calculate the period. So in this case, it would be 1 over 2 hertz. So that's just 0.5 seconds. And you can see that's true on the graph here. If this is 1 second for there, we can see that this right here would be half a second, 0.5 seconds. And it goes the other way. So if we know that that's half a second, the frequency would be 1 over a half. And that equals 2 hertz. Do you have a question?
So a cycle would just, so the cycle on top where you like wrote the 1 cycle,
Yeah.
is there a defined distance we calculate for seconds? Can you like see how far you would have to do to get a cycles per second calculation?
Yes. So when we look at, if we're looking at this on an oscilloscope, we'll be able to tell what distance corresponds to how long, what amount of time. Yeah. And we'll talk about that in just a second. So yeah, so any other questions about this? All right, so those are the 3 main things that we control on a function generator. We control the shape of the signal, the amplitude, or the voltage of the signal, and then also the frequency of the signal. So that's a good point to kind of segue over and talk about the oscilloscope. So let's transition and talk about that for a minute. So, but again, the most important thing about a function generator is that it creates these electrical signals. So let's talk about oscilloscopes. So an oscilloscope takes pictures of electrical signals. Well, okay, so an oscilloscope measures electrical signals over time. But it's really like taking pictures. When I think about an oscilloscope, I really think about it like a camera for electrical signals. Literally, it's actually measuring these signals over time, but it's really like taking pictures of them. Okay, and there's a couple of ways that this metaphor works. So first of all, when you take a picture of a scene, you don't actually change that scene, right? You just capture it the way it is. And that's true about oscilloscopes too. When they look at these electrical signals, they don't change the signals. They just give you a picture of what that signal is doing. Also, when one of the most important features of a camera is that a lot of cameras have the capability to zoom in and zoom out. So you might start, if you're taking a picture of a landscape, say, you might start with a picture that's zoomed out so you can see the whole landscape and everything that's there. And then after that, you might notice something in your picture that looks kind of interesting. And then you might zoom in on that one interesting part so that you can get a better look at it and see it more clearly. Well, the oscilloscope does the same thing. It has essentially zoom controls on it. So you can zoom out and see a big picture of your signal, and then you can zoom in and look at one part of it to get a clearer look at just that one interesting detail. Okay? But and when you're taking a picture, when you zoom out, things look kind of small on that picture, right? But then when you zoom in, that thing that you're zooming in on looks really big on your camera screen. But did the thing actually change in real life when you zoomed in on it? No. Only the picture of it changed. So the oscilloscope is the same way. When you zoom out, your signal might look kind of small so that you can fit a lot of it on the screen. When you zoom in, it looks much bigger and you can see it in much more detail. But you didn't change the signal itself. You're just changing the way you're looking at it, like zooming in with a camera. Okay? So that's why I think about the oscilloscope like a camera for taking pictures of electrical signals. So there's a couple of things that you can control on the oscilloscope. The zoom feature being the most important one. Why don't I switch over and actually show you some of these things in action? Because, well, actually, yeah. Before we do that, let me just talk a little bit about the display on an oscilloscope. So when you look at an oscilloscope screen, it looks something like this, and it's got these little dashed lines on there. So dashed lines, there are vertical dashed lines, and there are also horizontal dashed lines. And these dashed lines help us to make measurements of the signals on the screen. So each one of these little squares, so these dashed lines together make these little squares or rectangles on the screen. So each one of these little rectangles is called a division. So it's like a little box. And the oscilloscope will tell you how big this box is. So down at the bottom, there will be an indication for volts per division. That's the height of the rectangle. And there will also be a little indication for the time per division. And the time per division is the width of the rectangle. So this is how we can actually measure a signal on our screen. So let's say that we were looking at this screen and we saw that we had a sine wave here, and it was going something like this. And say we had um, two volts per division and 3 seconds per division. Okay? Yeah.
So, I didn't know if you wanted to explain it more, but I can answer it.
Yeah. Okay. So what would be your answer?
Since you're measuring it based off the center line, since you need a 0 point, I would believe, it would be 6 volts, or sorry, 4 volts on each side because it's 2 from the center.
Right. Right. So it's 2 up there and then 2 up there. So yeah. So if this is 0 volts, then this top would be at 4 volts. Perfect. And then down here, what would that be?
Also 4 volts.
Well, yeah, but this would be negative
Negative 4.
4 because we're below 0. Yeah.
And then because you're 2 squares wide, it would be 6 seconds.
Almost. So yeah. So this would be 3 seconds there.
Oh, okay.
Yeah, and then another 3 there. So that would get us to half of the wave, but then we want to get back to where we started, where the wave is kind of going up from 0. So that would be 4 of these divisions. Yeah, so that would be right 12 seconds altogether. So for this wave, the period would be 12 seconds, and the amplitude from the highest peak to the lowest peak, we call that the peak to peak amplitude, or voltage peak to peak.
Does this have to do anything with sine or cosine?
I mean, hold on one second. So V peak to peak here, we're going from 4 volts to minus 4 volts. So that's 8 volts total. So that would be 8 volts. So you can use this, you can measure the peak to peak amplitude of any signal, whether it's a sine wave or a triangle wave or a square wave. The peak to peak amplitude is just the voltage from the highest peak to the lowest peak. Okay? Yeah.
So would that technically be the total voltage of your circuit?
I mean, it depends on where you're measuring it. So if you're measuring this coming out of the power supply, then that would be the peak to peak voltage for the power supply. But you could also make this measurement at other points in your circuit. Yeah. Yeah.
Could you go over that again? How you got that before he answered it?
Yeah. So, okay. So when you set up your oscilloscope screen, however you set it up, it will tell you at the bottom how many volts per division you have and how many seconds per division you have as well. So in this example, I just said that we have 2 volts per division and 3 seconds per division. And that means that each one of these little squares, or rectangles rather, is 2 volts high and 3 volts wide. So,
3 seconds wide, right?
yeah, I'm sorry. Yes, thank you. 3 seconds wide. So this distance there would be 2 volts from the top to the bottom. and 3 seconds from side to side here. So that's what each of these little rectangles represents. 2 volts high and 3 seconds wide. So then to find the size of our, or the amplitude of our wave, we count how many of these little rectangles there are from the very top to the very bottom. So in this case, there are 4 rectangles from the top to the bottom, or as close as I could draw it there. Yeah, yeah. And then we counted, so that's how we found our amplitude. So if we call the middle of this wave 0, then we go up by 2 divisions. That gives us 4 volts at the top of our wave. And if we go down by 2 divisions, that gives us minus 4 volts at the bottom. So then the total amplitude of the wave is 8 volts from the top to the bottom. And then for the time, we looked at the amount of time for one period. So one period, we said, is from one point on the wave to the same point on the next wave. So that would be from there to there. We counted the number of boxes. We said that there's 1, 2, 3, 4 boxes for the period, and each box is 3 seconds. So the period then is 12 seconds. Yeah.
Will the measurements always hit the bottom of the next rectangle and like a full rectangle?
No, not necessarily. Sometimes you just have to estimate. So yeah. So yeah, you just this is a good way of getting close, and then the oscilloscope actually has some built-in measurement functions that will give you an even more precise measurement. And then as a bonus here, if we know the period, can we calculate the frequency of this wave? Yeah. So we would just use that formula over there, and we would say that the frequency is 1 over the period. So in this case, that would be 1 over 12 seconds. So does anybody have a calculator? What does that come out to be?
.0833.
Okay, so 0.0833 hertz. So that would be the frequency of this wave. So we could use the oscilloscope to measure the period, and then from that we could calculate the frequency. Okay, so those are the types of measurements that we can take on the oscilloscope. So any questions about that? All right, then let's fire up the projector and actually see how to use all of these controls. Actually, we can. While that's firing up, I want to talk a little bit about cables. So each different piece of equipment has its own cable. So this is the cable that we use for the function generator. It has it has 2 clips on one end. They're red and black. They're both alligator clips. Okay, and then the other end is kind of a BNC. It's this type of connector called a BNC connector. So let's see what this looks like on our screen here. So this is the cable that we use for the function generator. Okay. Now, to plug it into the function generator, what we're going to do is the function generator actually has a couple of different ports where you could plug this in. We want the one that says output, okay? So you look for the port that says output, and that's where you need to connect your cable. If you connect it to the other ones, it's not going to work. So the way that you make the connection is that you take the cable, the little port has little bumps on it that kind of stick up on the top and the bottom, and the BNC connector has these little channels in it. So you have to line the bump up with the channel, you push it in, and then you twist the connector. So again, you line up the little bump with the channel, you push that in, and then you take this little collar on the BNC cable and you twist it and make a good connection that way. And then that is connected. So now, the oscilloscope cable looks like this. So the end of the oscilloscope cable looks like this. It's got a big probe on it. That's going to be your signal probe, and then the other end of the it's also got this little clip on the end of the oscilloscope cable, and that's your ground lead. So you're going to connect this to ground, and you're going to connect this probe wherever you want to actually measure the signal. The other end of the oscilloscope cable is also has a BNC connector on it. Okay, so since this oscilloscope cable has the same type of BNC connector as the function generator cable, people always think that they're interchangeable. You can use one for the other, but they're not. Okay, this is the type of cable you need to use for the oscilloscope. The other type of cable needs to be used for the function generator. If you switch them around, your measurements might be off, because the oscilloscope cable has a very specific resistance and capacitance to it. And if you try to plug the function generator cable into the oscilloscope, the resistance is going to be off, the capacitance is going to be off, and it's going to throw off your measurements that way. Okay? So you need to use the oscilloscope cable for the oscilloscope. Now, the oscilloscope also has several ports where you can plug things in. On the bottom here, you can see that there's this row of ports, and these ports on the left have numbers. So this is 1, 2, 3, and 4. Each number corresponds to a particular channel. So this is a 4-channel oscilloscope. That means it can measure 4 different signals at the same time and display them all on the screen. Now, we are only going to be measuring one signal today, so you're going to plug this into channel 1. So again, you find the little knobs or bumps on the oscilloscope port. They're going to be on the top and the bottom. You line those up with the little slots in the BNC connector. you push it in, you twist the collar to make a good connection, and then you're all set. Okay. So now, like I mentioned, these instruments are used for testing circuits. So normally what you would do is you would set up your function generator and you would create some type of signal and then connect that to the input of a circuit. And then your circuit would do whatever it's supposed to do. And then you could use your oscilloscope to measure the output from that circuit. So that's how oscilloscopes and function generators are used in the real world. But for today, what we really want to do is we just want to become familiar with these two instruments. So today, what we're going to do is we're going to connect the function generator directly to the oscilloscope, so that we're just using the oscilloscope to measure exactly what's coming out of the function generator, just so that we can see what the generator is actually creating. And we can play around with the controls on the oscilloscope and learn how those work as well. So normally you would hook these up to a circuit, but today we're just hooking them directly to each other to see how they work. Okay? So that's what we're going to do. We're going to take, now that these cables are connected to the instruments, we're going to take them and hook them to each other. So we're going to take the black lead from the function generator and connect it to the ground of the oscilloscope. So just clip those two things together. And then we're going to take the red lead from the function generator. This is the lead that actually creates the signal. And then we're going to connect it to the probe on the BNC, or on the oscilloscope. The way that you access the probe on the oscilloscope is that it has this little sleeve around it. So you grab the bottom of the sleeve and you pull backwards, and then that exposes this little hook at the end of the connector there. So you're going to do that, and then you're going to clip the function generator lead onto that little hook to make a good connection. So now we've hooked the function generator directly to the oscilloscope. So now we can actually power these on, turn them on, and see how they work. So one of the most confusing things about the oscilloscope when people first start to use it is, how do you actually turn it on? If you look at this thing, there's no on switch on the front. So people spend longer than they probably want to say just trying to figure out how to turn it on. The trick is that the on switch is on the top. You can't really see it from the front. It's on the top. So you got to turn it on there. And then the power button for the function generator is right on the front there. So you just power that up. All right. So let's talk about the controls for the function generator first. So we said that we could control three main things about the signal. What was the first thing that we could control about the signal? The shape, exactly. So if you look down here on the function generator, we have buttons that have different shapes on them. So we've got this button, which is for square wave, the middle one is for triangle, and the one on the right is for sine wave. Okay, so so right now, you can see that we have a triangle wave on the oscilloscope. So if we push one of these other buttons, say I push the square wave button, now you can see that we're creating a square wave. Or if I push the sine wave button, now we're creating a sine wave. That makes sense? Again, these are all controls on the function generator. So these are actually changing the signal itself, okay? Because the function generator is the instrument that creates the signal. So when I push these buttons, I'm actually changing the signal that's being created, okay? So that's the shape. What was the second thing that we could control? Amplitude. The amplitude, perfect. So down here, there's this knob, it's labeled AMPL. So that's the amplitude knob. If I turn it one direction, you can see the signal getting smaller. If I turn it the other direction, the signal gets bigger. So that's how we control the amplitude. Make sense? And then what was the last thing we could control? Yeah, the frequency. Exactly. So there's actually two controls that work together to set the frequency. So the first one is the frequency knob here. So over on the left, there's this frequency knob. If I turn it one way, the frequency gets lower. And you can see that the period is getting bigger there. It's taking longer to complete one cycle of the wave. If I turn this knob the other way, the frequency gets higher. You can see we get more periods on the screen. So that's sort of the fine tuning for the frequency. But that works over kind of a limited range. And we want to be able to create signals that are very high frequency and also very low frequency. So we actually have these buttons along the top of the function generator that set the frequency range. So right now, so you can see there's a number on each of these buttons. So 1, 10, 100, 1,000, 10,000, and so on. These buttons are the frequency range. So right now we're in the 1,000 hertz range. The way that you get the actual frequency is you take this range and you multiply it by the number on the dial. So we're in the 1,000 hertz range and the dial is at about 1.5. So what's our approximate frequency?
1,500.
Yeah, about 1,500 hertz. 1,000 times 1.5 is 1,500. If I move that and put us in the 100 hertz range, what would be our frequency now? 150, exactly. So, and if I put it down at the 10 hertz range, we'd be at 15 hertz. So that's how you actually set the frequency. You set the range, and then you multiply it by the number on the frequency knob. Okay? So that's how we actually set the frequency there. So any questions about that? All right. So those are the controls on the function generator. Again, we can use these buttons to set the shape. We can use this knob to set the amplitude. And then we can use the range and the knob to set the frequency. Those are the main three controls. So any questions about the function generator before we move on? All right. So then let's talk about the oscilloscope for a minute. So we said that the oscilloscope it's really like a camera that's taking a picture of these signals. So it's not changing the signal, it's just giving us a picture of the signal. And we said that there are two main indicators on the oscilloscope, or two main things at the bottom that tell us something about the signal. So down here is the volts per division. So right now this is set at 20 volts. Yeah. Right. Okay. So right now it's set at 2 volts per division. Okay. So if we look at this signal, it's almost exactly like the example I did on the board, right? There's 2 volts per division, and how many divisions are there from the very top of the signal to the bottom?
4.
There's 4. So how many volts do we have from the top to the bottom? 8, exactly. I could come back to my function generator, and I could change the amplitude so that it's more like that. So now, if I look at the oscilloscope, now how many divisions are there from the top of the signal to the bottom? 2. So how many volts do we have from the top to the bottom? 4. Perfect. So I can change that around. But now this signal is looking kind of small on the screen. If there were details in that signal, it would be a little bit hard for me to see them. So I might want to zoom in on this signal to see it a little bit more clearly. So the way that I can do that, well, a camera only has one kind of zoom. It zooms in or zooms out. That's the only control you have. With the oscilloscope, you actually have 2 separate kinds of zoom. You could zoom in the vertical direction, up and down. You can also zoom in the horizontal direction. So this signal is looking a little bit small in the vertical direction. So I want to zoom in there. So if I do that, if I want to control the zoom in the vertical direction, I can see that this section is the vertical section, and this is the knob that corresponds to channel 1. So if I want to zoom in the vertical direction for channel 1, I would use this big knob here. So if I turn that, I can see the signal getting bigger on the screen. Now, did I change the signal itself? No, exactly. This is like zooming in on the camera, right? The thing on the screen looks bigger, but it's just because you zoomed in. You didn't actually change the thing you're looking at. So here I didn't change it. But now it's taking up more divisions on the screen. How could it take up more divisions without actually getting bigger? Yeah.
Well, isn't it just a 2-dimensional zoom versus like a camera's 1-dimensional zoom, where it's like instead of zooming in both at the same time, both width and height, this is focusing on just showing the
Right. We're zooming in the vertical direction here. But remember before, when we looked at the screen, we had 2 volts per division. Now, when I zoomed in, you'll notice the volts per division has actually changed. Now it's only 500 millivolts per division, or half a volt per division. So let's check how big this is telling us that the wave is. Before, we said it was 4 volts peak to peak, right? Now we've zoomed in. So let's see. We've got 1, 2, 3, 4, 5, 6, 7, 8 divisions from the top to the bottom, and we have 500 millivolts per division. So how many volts do we have from the top to the bottom?
4.
Yeah, 4. So it's half a volt per division, and we have 8 divisions, so that gives us 4 volts. So just like before, the scope is still telling us that we have 4 volts peak to peak. So we can get the same measurement, but we can just be more precise about it now because we've zoomed in. Okay? Yeah. So before we were zoomed out, and we had 2 volts per division and only 2 divisions. So that gave us a total of 4 volts from the top of the wave to the bottom. Now, when we zoom in, the signal looks bigger on the screen, but the volts per division has actually changed. So now we've got 1, 2, 3, 4 volts, or I'm sorry, 4 divisions from the top to the bottom, and each one is 1 volt. So we're still measuring 4 volts from the top to the bottom. And if we do it again, now we've got 8 divisions, but only half a volt per division. So it's still showing us 4 volts. So we're making the same, we're getting the same measurement from top to bottom, but when we zoom in, we can be more precise about it. Okay? So now we've been zooming in the vertical direction. We can also zoom in the horizontal direction. So over here on the right-hand side, we have this horizontal section. And we have this horizontal scale knob. So if we turn this knob one way, we're going to start zooming in. And you can see that the more we do that, the more we zoom in. So I'm going to change the setting on the function generator here for just a second. All right. So we can also change the horizontal position. So this moves the wave left or right. So if I turn the knob in one direction, it moves the wave to the left. If I turn the knob the other way, it moves the wave to the right. This can be helpful for lining up your signal in a way that's convenient when you're measuring it. Okay. So let's look at this signal now and try and figure out what the period is for this signal. So remember, the period is the amount of time that it takes for one complete cycle. So you could say that a cycle starts here at the very bottom of the wave where the wave is going up, and then the period would begin again when you get back to the same spot at the very bottom of the wave. So this would be one period. And down here, the scope is telling us that there are 250 microseconds per division. So that's a quarter of a millisecond. So we have 1, 2, 3, 4 divisions, and a quarter of a millisecond per division. So how many milliseconds for a period?
1.
Yeah, 1 millisecond. So this wave has a period of 1 millisecond. And so period equals 1 millisecond, and that is the same as 0.001 seconds. So if we wanted to calculate the frequency, we would say that frequency is 1 over the period. So that is 1 divided by 0.001 seconds. So what does that come out to be? What would that be?
10 hertz.
Almost. I think that's 1,000 hertz. So the frequency here should be about 1,000 hertz. And if we look down at the very bottom corner of the display here, that shows about 1,000 hertz. Okay? So that's how we can control the oscilloscope. We can zoom in the vertical direction using this knob. We can zoom in the horizontal direction using this knob. And we can move the wave left and right using this position knob. Okay? So any questions about that? Yeah.
Sorry, I missed. Where is the time period actually shown on the oscilloscope?
So
Where it's
in this case, right now the period is not being shown. But like I did mention earlier, that's a great question, that the oscilloscope does have the ability to make these measurements. So if you want to look at the measurements on the oscilloscope, you can push this button at the very top, which is labeled measure. So we can push that. And then right here along the side shows the measurements that are being made right now. So right now there are no measurements being made. So the way that you can change this is you can push one of these buttons and then choose what you want. So you can choose the source. Right now it's channel 1, but if you wanted a different channel, you could push this button to cycle through the different channels. So we want channel 1, and then you can choose the type of measurement here. So right now there's none, but if we push this, we could measure the frequency, and then this shows the value that's being measured right there. Or you could measure the period. So right now this is the period that's being measured. And then when you're happy with the type of measurement that you want, you push back, and now that measurement is shown in that spot. And if you want, you could go down to the next spot and choose a different type of measurement. So maybe down here we want the frequency. So now we're making those different measurements. And really there are many different types of measurements that you could choose. So there's frequency, period, mean, which is average, peak-to-peak amplitude, RMS, that's a different type of amplitude measurement, the minimum value, maximum value, rise time, fall time. So all of these different types of measurements that you could choose. You can just pick the one you like, and then when you are happy with it, you push back, and then it selects that and shows that on the screen. Yeah?
Can we go over again how you got the period to 1 millisecond?
Yeah, so how I calculated it, or how I set it on the actual signal, or?
How you set it on the signal.
Okay, so what I did is I played around with the controls on the function generator, because remember the function generator is the instrument that's actually creating the signal. So what I did is I put the generator in the 1 kilohertz range, and then I set the frequency to about the knob to about the 1 position. So then the frequency is just 1 times 1,000, or about 1,000 hertz. And I mean, you can tell that there are numbers written on this frequency dial here, but they're kind of coarse. It goes from 0.9, and then the next one is 1.2. So you're not going to get really precise measurements by looking at that dial. So if you want a really precise measurement, what you can do is you can actually look at the screen of the oscilloscope while you are changing the controls on that function generator. So say I wanted a frequency of 500 hertz. What I could do is I could look at this frequency up here, this frequency measurement, while I turn this dial. So I could turn this down, and now I'm at 670, 589, and I could keep going until I get the actual frequency that I want. Oh, I overshot a little bit. I'll come back. So that way you can get a much more precise measurement than you could just by looking at the dial. So that's really what you would want to do if you were looking for a precise frequency. Does that make sense?
Yeah. Could you also go over how you calculated it too?
How I calculated the frequency?
Mm-hmm.
Okay, yeah. So this was up around 1,000 hertz. So then what I did was I looked at so what I actually measured was the period of the signal. So the way that I measured the period is I counted how many divisions there were in one cycle. So I looked at the bottom here, and I saw that one complete waveform could be from the bottom of the one wave to the bottom of the next wave. So from here to there are 4 divisions, and each division is 500 milliseconds. I'm sorry, 250 microseconds. Each division is 250 microseconds. That's a quarter of a millisecond. Yeah, so 4 of those gives you 1 millisecond for the period, and then the frequency is 1 over that, which is 1,000 hertz.
Got it.
Yeah,
Thank you.
sure. So that's how the controls work on the function generator and the oscilloscope. So any questions about that? All right, then let's do a preview of today's lab. So the lab is in the lab book, and it's starting on page 123. So the first part of the lab says that we want to create a triangle wave that's at 1,000 hertz and 4 volts peak to peak. So, so that's what we've done really here. We created a triangle wave. We set it to 1,000 hertz, and we made it 4 volts peak to peak. Now, the next thing it says is to measure and sketch the waveform. So the first thing we want to do is we want to set this up so that it looks nice on the screen. So, so what we can do is we can adjust the oscilloscope screen so that the wave looks nice. It might look something like that. Okay, so there are a couple things that we want. We want to be able to make sure that we see the top and the bottom of the wave, and we want to see at least 2 complete periods of the wave on the screen. Okay, you need to see the top and the bottom, because if you couldn't, you wouldn't be able to know how big the wave actually is. You also need to be able to see 2 complete periods, just so that you get a good sense of what the wave looks like, and you make sure that you're seeing exactly what's going on. Okay, so we set this up like this so that it looks good on the screen, and then we want to sketch that in our lab book. So, so to sketch that in the lab book, we want to do a sketch that looks something like this. Okay, so it says include the voltage and time settings as well as the 0 level and trigger arrows. Okay, so your sketch might look something like this. So you would draw the wave the way that it appears on the screen. And I want you to be careful about this. I don't want you to, if it's this triangle wave on the screen, I don't want you to just kind of draw a rough triangle. I want you to actually make sure that you have the correct number of divisions. So if we look at the screen here, we can see that it's 4 divisions from the top of the wave to the bottom. So make sure you do that. And then you can see that the triangle wave starts kind of 2 divisions down from the middle here, and then it goes 2 divisions up and 2 divisions over for the first point. So when you draw that in your lab book, that's what I would do. So I would mark the first point right down here, and then mark the top of the second point there, and then draw a line between them. So that the idea is that if somebody were to come back and look at your lab book later on, they'd be able to look at your picture and look at the volts per division and the time per division, and actually tell, just by looking at the wave, how big that wave actually is. Okay? So in addition to drawing it clearly and writing down the volts per division and the time per division, this also says measure the peak-to-peak range on the sketch. Indicate and measure. So that's like what we have over here. So this would be 4 volts peak to peak. It also says to include the 0 level and the trigger level arrows. Okay? So let me talk about those for just a second. So up here on the screen, we want to know where 0 volts actually is. So that's what this little arrow over here on the left is. That little arrow indicates 0 volts. Now, somebody out there is going to say, hey, wait a minute. That's not 0 volts. That says 1. That must be 1 volt right there. No, that little 1 stands for channel 1. Okay? So that arrow is the 0 level for channel 1. If we had other channels, they could have their own 0 levels. Okay? Now, the reason that this is important is because that 0 level doesn't have to be right in the middle. You could have a different wave that looked exactly the same. Maybe it was also 4 volts peak to peak. But maybe the 0 level for this wave is down there. So if that were the case, and the 0 level were right at the bottom of the wave, what voltage would we have up here at the top? 4. Yeah, 4 volts. So you could have a wave like that. Or you could have a wave that looked exactly the same. It was also 4 volts peak to peak, but the 0 level could be, it could be up here. And maybe this is, you know, there's a 1 volt, the 0 level is 1 volt above the top of the wave. So then what would the top of the wave be at? Minus 1 volt, exactly. And where would the bottom of the wave be? Yeah, minus 5 volts. Because we're down 1 there and then down 4 more. So the wave could look exactly the same on the screen, but if the 0 level is in different points, it means that, you know, the voltages are different at different spots on that wave. So that's why the 0 level is important. So you need to mark that. Then the last thing is this trigger level. So the trigger level is this arrow on the right-hand side. So what's happening with this oscilloscope is that it's really taking pictures of this signal over and over again. So this trigger level tells it when to take those pictures. Basically when the signal crosses the trigger level, that's when the oscilloscope takes a picture. So this trigger level has to be between the top and the bottom of your wave in order so that that wave crosses the trigger level and tells the oscilloscope to take a picture. You can adjust the trigger level with this level knob up here. So we can turn the knob, and you can, if I turn it one way, you can see that that little trigger level arrow is going up. If I turn it the other way, the trigger level arrow goes down. Watch what happens if I move this trigger level so that it's above the top of the signal. Now the signal is kind of jumping all over the place. It's not synchronized anymore, okay? Because the oscilloscope doesn't know when to take the picture. So it's just taking pictures at random times. Sometimes the wave is over on one side of the picture, other times the wave is over on the other side of the picture. So if you see your oscilloscope and you look at the picture and it's jumping all over like this, usually means that the trigger level is out of place. So remember, you need to move that trigger level so that it's between the top and bottom of your signal.
Anywhere in between?
Anywhere, yeah, anywhere as long as it's between the top and bottom. So I could have it up here close to the top, and that's fine. I could have it down here close to the bottom, and that's fine too, as long as it's somewhere between the top and the bottom. Okay, I usually like to have it close to the middle, just in case the signal changes size or stuff like that. But it can be anywhere. Yeah. So when you are filling out your lab, you want to make sure that you draw your trigger level and your 0 level on your graph as well. Now, many of the graphs will also ask you to indicate the period for that graph. So you would want to draw something like this. So you would show where the period is and then the amount of time for that period as well. Okay? So you're really just going to do a series of these different signals for this lab. So you'll do that one, and then let's see, the next one is a triangle wave, but now it's at 8 volts peak to peak, and then a sine wave at 1,000 hertz and 8 volts. So you get the idea. So you're doing, I think, 5 of those for the lab, and then that's it. So any questions about that? All right. And I think that you should be able to get through this lab relatively quickly, so I would recommend that at the end of the lab you bring up your lab books to get your grades entered, if you haven't done that for a while. Okay? All right. So let me take attendance and then I'll let you go.